part 2. So without DG calculation, load flow and load flow are same in nature. I mean, the load flow is doing same. The difference is that in load flow 1 and load flow 2, we have to introduce the injection. So either it can be of a real or reactive injection or both. But that's the difference between without DG. In without DG, there is no injection, and in load flow 1, load flow and load flow 2, we have injection. So what is optimization do here? Optimization helps us to find the best combination, best pair of location and size, and then we have to put that pair into our consideration. Okay. So here is the main file. Main file is just redirecting into the ABC file. So in this ABC file, initially we have to put number of DGs, and here is the let me left click here and click on continue. Okay, so we can put between any number of DGs. For example, let's consider 2. Continue. Okay, and let me take here the real and reactive power. Okay, consider. Oh, sorry. Click on step and now put 3. Okay, so now we have considered real and reactive power injection. Here is the problem definition. So in problem definition, so here the cases represent type of DGs. So for type 1, so the case 1 represent type of actually the injection type of DG. So case 1 will for only real, and case 2 for only reactive, and this one is for both real and reactive power injections. So a number of DGs will be considered here, that is actually 2. So in problem definition part, we have to uh, give our optimization algorithm the minimum and the maximum. So here we have number of decision variables will be around for example. Okay, so in this case we have here number of DGs that are 2, so multiply by 3. So we have decision variables here are 6. So in problem definition part, we have to give input and output of each decision variable. For example, for the power of real and reactive, we have minimum 0 and maximum is 3000 kilowatts, 3 megawatt, and the location will be around 1 to 69. So in case of 33, it will be from 1 to 33, and this is the real power real maximum size, and this is the reactive maximum size. Okay, so for example, let me move my cursor here and let me click on continue here. In this case, both first and second cases will be skipped, and let's continue to 3. Okay, so here I have variable minimum, that is around 4 zeros, means first 2 will represent reactive powers that are minimum 0, and next 2 were the okay. So here you can see 4 zeros. So first 2 0 will represent the real power are zeros considered, and next 2 are the reactive power zeros, and next to 1 1 represent the location for 1 DG and second DG. So let's continue to the maximum of their size. So 3000, first two 3000 will represent the first and second DGs with real powers maximum 3000. So next two will represent 3000 of reactive, and at the end there is 69, that is the maximum location. So you can also change the them according to your requirement. If you want to change the minimum, you can also just you have to make it 1000 or any number. Okay, and next we have here let me run the program again. 2 and 3. Okay. And now allot the maximum iterations that should be around 100. Previously I was actually testing it, that's why I put 10, so minimum time is considered. And there is next population size, colony size, that is considered to be number of DGs, so in this case it will be 80. You can also adjust this a bit. And non-local base, these are equals to the number of population. And this is the abandoned some abandonment limit parameter, so which you have to adjust. There is a mathematical calculation behind this, and it will be multiply of 0.6 to NVR and pop. Okay, and then there is the initialization. So initially we have to put input the position and the cost. Here the cost represent actually the power loss. uh, Power loss real, we consider real power loss as the cost here. Initialization population array. Okay, initially maximum cost is defined as infinite. So whenever we find any value that will be less than infinite, and then we will uh, overlap the infinite number. Okay, so here let me show you one thing. Let's click on continue. Let me break the program and run again. 2 and 3. Okay, so here based on our minimum and maximum and the number of decision variables, we have to define some initially we need some random positions between minimum and maximum. So let me click on. Okay, now pop I, it means pop and pop I position. Okay, let me restart the MATLAB. I actually there is a problem with the workspace here, so let me just restart the MATLAB. So it's routine that MATLAB creates some problem whenever there is seems to be a problem. Just restart the MATLAB. Okay, so here you can see that we have here section of workspace. Oh, I think so. Maybe I have just okay this thing. Okay, we were previously at this stage. Let me click on continue. So here in pop there are different variables. Dot means we have variable inside another variable. So pop I population, that is actually pop. So first variable we have these numbers. So here we have based on our decision variables we have 6 parameters. So first two will be the real powers, next two will be the reactive powers, and at the end 23.01 and 65.3 65.63. So that will be round off, and the last numbers will be the locations. So we have this data, and this data we have to now inject into our load flow program. So now let's open the load flow program. Okay, so let me left click here. Okay, and okay, the this data is now we are putting into our load flow program, and that is uh, actually the injection we have to do. Okay, so pop by position we have the data which I show you previously inside this population variable, and then we have a number of number of DGs and type of DGs. So let me click on step. Okay, and now here in this file load flow have to done the injection in the load flow program. So type of DG 3, number of DGs 2, and in DG exactly same thing which I show you previously in the pop I position variable. And now initially PGQG, this is the generation or injection is putting to 0, and now we have to here consider the case 3. So let me click continue here. Okay, click on start. Okay, so PS is actually the first number that is actually the real power. Okay, let me move my cursor. So first two numbers 548303 are the real power injections. So we are putting the real power injections. So let me show you the PG and QG. Here PG is all around 0, QG is all around 0. So here we have to put the numbers of DG data, this data at the location. So we have to put 548 and a real power and 604 reactive power at the location number 23. Okay, let me click on continue. Okay, now let me click on yes. So at the location number 23, you can see that there is a 548. Previously it was 0, and at the QG we have 604. The other injection is at the end. Let me also PG. So the second injection is at 66 bus, and that is that one. Similarly, you can also verify that the injection is QG. And now exactly the same thing which I have previously explained in the without digit calculation. So it have to calculate the exactly same code. So I have to calculate the n nodes. Let me go through again. So initially it will be from bus to bus, and then calculating the n nodes, and then in next step I have to calculate the branches, and then uh, rearranging the branches, and then making the each branch into vertically, and then representing it, rearranging it, and then starting of the multi-current program, calculating the current between the buses, the line current, and after that rearranging, and then calculating the voltage profile through the line current and bus current. Okay, and after that it have calculated each and everything, and at the end uh, voltage deviation and the uh, PL is actually the real power loss. So I have to needs to sum up this thing. Click on continue. Okay, so after sum up, now FIT is actually 180. So real power loss sum at each bus, and the voltage deviation is considered as the cost function. So click on step, and now we are back into this main program. Previously we were uh, going from this program, this is instruction file, to load flow, and now we are back into the load flow file, and now we have to save that cost. Click on step. Okay, so now let me again open the population and against. So it means we have done injection of these numbers into load flow program, and load flow program calculate the cost for us, that is 180.62. So for in this way for each let me now click on the continue. So this loop will repeat for 80 times, and 80 times it will generate different numbers, and cost will calculate the click on continue. Okay, and now let me show you both. And now here we have these kinds of entries we have done into the load flow program, and load flow program have calculate the cost based on the injection we have made here. So from these numbers you can get an idea that there are some good numbers and there are some worse numbers too. So it's now the job of the optimization algorithm to find which one is the best, and in which direction we have to get numbers to get the best solution. And now we are into the ABC main loop. Okay, and here is some calculation for the K, and there is a research or scientific research behind these things. So how to calculate these things. So it's a standard code, so we have to just uh, needs know how the program is running, and there is a define acceleration coefficient. Okay, okay, and now previously we generate random numbers, and now at this stage we have again finding another inputs, finding the best inputs that we have to incorporate or into our load flow program. Okay. Okay, so now newbie positions. So let me newbie, and now at this time we have this position, and this position is created again first to real reactives and then the locations of the DG. So this I mean numbers created by these numbers are created by the defined acceleration coefficient and the randomly k numbers, and then again representing assigning the limits and then evaluation. And now again we have to put that numbers. Let me again show you the process. Just let me click here. Okay, let me, okay, so in this step we have the numbers inputs. You can say that load flow is the program and this is the input. We have put this input and we will get this output. So we have up to now we have put input into the load flow program, and against that the load flow program calculate the power. Again this is the verse, but by step here you can see that this is the uh, real power. This is the power which we have to inject here. So in this way it will calculate the cost. Let me click on step newbie cost, opening the newbie, and then cost is 242, which is not a good at all. And now we have to compare that which one is the best, and then this will have process have to repeat for all the populations, and then finding the best number, best cost newbie into pop I, and then finding the best number we have to overlap the pop I. Let me click on continue. Okay, so here is the pop. Let me open that. Okay, so in this way this is the main loop, and now we are updating our population again. So previously we have the populations initially, and now 180 to 48. Previously we have calculated by the random numbers, and now we are updating. If we are getting the better number, then we have to overlap it. And then there is a calculate fitness values and selection probabilities, just including that ones. And now onlooker bees. So now we have introduced the onlooker bees, and again there is a roulette wheel selection. This is the code based on our previous history. Roulette wheel selections helps us to find the better inputs, you can say, or better inputs, better numbers which we have to put into our objective function to get the better results. Again here at the population putting the limits, and again we are here to let me click on continue here. Okay, now at this stage again newbie position, let me open that newbie and position, and now at this time we have generated these positions. Previously there is a cost against it, and okay, let me open it. Nope, 146. Okay, okay, so 146 at this point newbie cost is let's find out. And now newbie cost is and now get 154. So in some cases it will get better, and in some cases it will get worse, so I have to skip the worse. Okay, now let me move cursor to I to the 77 population, and I to cost population, and then okay, now we are at this point. So if we get the better numbers, then we have to replace this thing. Okay, so and in next step we have to get into the scout bees, and then scout bees will find the best results. Okay, so at the end of this program we have the best values inside of our best solution cost. Let me click on continue here. So in this way, scout bees, and at the end of this program we have the best solution dot cost. So up to now we have the position means the real reactive powers and the location, and the cost means the best cost ever we have met. So in this way, at the end of this program, let me click on continue. Now the algorithm is finding the against each iteration. This is the maximum iteration. Against each iterations, it finds the best number which he have get. Through there are different stages. Scout bees will generate another input, okay, and the onlooker bees will generate another input. So each bees have different types of nature, and they just like you consider that we have heard of bees, and one bee when finds a flower, he convey the message to another bee that he finds at specific location and of specific size. He have to travel and the send the information to another bee. So that's how ABC works. Onlooker bees have its parameters to find the input, and then they will convey the message to the scout bees, and scout bees will evaluate the process and then find the best solution. So let's wait for the end. Okay, at the end of this program we have at the end of this program we have find the location and location of the DGs, I mean the real reactive powers and the locations which we have to put, and then we have to put that numbers into our load flow file. Means load flow 1 is used to uh, is used in the used by the optimization algorithm, and through load flow file and optimization algorithm we find the best solution. And when we will find the best solution, then we put that input into the load flow 2 file to make a comparison of the results. So after that I will go into the load flow 2 file. Okay, let's finish the program. Okay, so here I have get the plot. So this is the plot get from these lines of instructions, these ones. Uh, Here the plot is done, and now let me best solution, and this is the solution location and size we have calculated up to now, and then the cost is 7.24. So this cost is not actually the real and reactive power, because in this cost we have included voltage deviation. Okay, so now let me click on the step. Okay, now I have put the click on step, and now again the DG is the first two will be the sizes of reals, then reactives, and then locations. Okay, so at the end of this program there is a plot for the voltage profile, and then there is a power flow and the P loss, and at the end there is a comparison between without dg.m, that is actually I have explained previously. So in this way this program works. Okay, so after that let me move my cursor here and let me click on continue. Okay, so it shows some parameters here, and then there is some plots, voltage profile, and then there is power loss and voltage profile, and these plots have been done here. At the end it have to print other numbers. So here we have to consider case 3, so this will be represented printed here, so here you can get an idea about it. Okay, thanks for watching, and if you have any other question you can ask.